Alright, so in this video we're going to talk about one particular method of expressing the composition of a molecule in terms of the atoms that, or the elements that make it up, or the atoms of those elements. And that way is by something called mass percent. Okay. Some of you may have seen something like this before. Some of you may have not. It doesn't matter. So one question might be, what is the mass percent of each element in glucose, C6H12O6? So the first thing we have to understand is, well, what does mass percent mean? Well, of course, percent means something out of 100. And as you would imagine, mass means something to do with grams. So presumably something to do with the molecular weight of this. And that's exactly what it does involve. And then the question doesn't specifically say which elements we're looking for, but it does say each element in glucose. So therefore that implies carbon, hydrogen, and oxygen. All right. So in other words, we have to find for this molecule the percent by mass of carbon, percent by mass of hydrogen, and the percent by mass of oxygen. So that's what we're going to do. So the first step in this sort of calculation is always the same. Because whenever you do a percent calculation of something, you've got to have something on the bottom and something on the top. And ordinarily, the bigger number is on the bottom, and then the smaller number is on the top. In this case, we're going to calculate the mass of the whole molecule, and then separately figure out the mass of carbon with respect to the mass of the whole molecule, then the mass of hydrogen with respect to the mass of the whole molecule, and then the mass of oxygen with respect to the mass of the whole molecule. So let's do the molecular weight for glucose first. Alright, so that molecular weight of glucose. Well, we know we have 6 carbons. Each carbon's got an atomic mass of 12.011 grams per mole. Each hydrogen, of which there are 12, has an atomic mass of 1.008 grams per mole. And then for the 6 oxygens, each one's got an atomic weight of 16 grams per mole. So 72.066 for the 6 carbons, 12.096 for the 12 hydrogens, and then 96 for the 6 oxygens. And if we add all this up together, what we get is that there, then that there, then that there, and then that there. Okay. What we end up with is a molecular weight of our glucose of 180.162 grams per mole. So all these units here, these are all in grams per mole. Now, believe it or not, we actually have everything that we need to correctly answer the question now. We have the mass of the entire molecule, and then we have the mass of each individual species, with the idea being that all 3 mass percentages are going to add up to, obviously it's going to be 100. All right. So let's do the carbon first. Percent by mass of carbon. Well, the mass of the carbon is right here. All right. We're going to assume we have 1 mole of everything. So therefore, in that 1 mole, we have 72.066 grams of carbon. All right. That's going to be divided into the mass of the whole molecule. All right. So we've got the mass of carbon on top, the mass of the whole molecule on the bottom. And because this is a percentage, it's all multiplied by 100, giving us, funnily enough, exactly 40.0%. That means of this whole molecule, 40% of its total weight is made up by carbon. Now, as you would imagine, because hydrogen is so much smaller, its percentage is going to be smaller as well. So the mass of those 12 hydrogens are 12.096 grams. Again, divided by the weight of the whole molecule. And once again, multiplied by 100. Gives us a percentage that is indeed much lower than 40%. It's actually 6.71%. All right. Which is not really a surprise, considering that this number is considerably larger than this number. Okay. Now, if you add up these two, we got 46.71%, which means that our oxygen is gonna have to make up over half of the weight of our glucose. And this is a good way to check that we're actually doing things right and we're not messing. Oh man, I did it again! Bloody hell! I've got to put my thinking hat back on. I don't know where it went. All right. So the mass of the oxygen has to account for over half the weight of the molecule. And as you can see from the numbers that we're doing here, that is more than likely going to happen. Because 96 is bigger than both 72 and 12. So therefore it's going to account for a larger mass than these two. In fact, 96 is larger than 72 and 12 combined, so it should account for a larger mass than both of those combined. Which, you know, shouldn't really be a surprise based on the percentages that we currently have. And that's exactly what we see. We got 53.29%. All right. So therefore, the percentage of carbon is 40.0. The percentage of hydrogen is 6.71. The percentage of mass by oxygen, the percentage of oxygen by mass is 53.29%. We add all these up, although perhaps we should try and draw straight lines first. If we try and draw, alright, whatever. Add all these three up, and what we get, as should not be a surprise, 100.0%. Alright, so that is exactly how you calculate mass percent of something. Now, what if we were to go the opposite way? Alright, what if a question gave you a compound consists of 40% carbon, 6.71% hydrogen, and 53.29%? Calculate the molecular formula for it. Well, it's actually just exactly the opposite method that you're going to use. Let's say 40% of that is carbon. That means 40 out of every 100 units are carbon. Which means you can say, well, if I can say 40 units out of every 100 units, I can say 40 grams. I can say in that molecule I have 40 grams of carbon. And in the same way, I can say I have 6.71 grams of hydrogen. And in the same way, I can say I have 53.29 grams of oxygen. Now, I wasn't planning on doing this, so I hope I'm not going to run out of space. And then you want to convert each of these into moles, so you're essentially going kind of back the opposite, the way that we did before. We know that in 1 mole of carbon, that weighs 12.011 grams. 1 mole of hydrogen weighs 1.008 grams. And 1 mole of oxygen weighs 16 grams. So what we're getting here is we start off with percentages, percent by mass, and we're converting that into moles. So 40, I'm just doing this on my calculator here, 12.011. This is what happens when you start spouting stuff you didn't prepare for. 3.33 moles of carbon. All right. And so 6.71 divided by 1.008 gives me 6.66 moles of hydrogen. All right. And then 53.29 divided by 16 is 3.33 moles of oxygen. Now, we have a situation there where we have C 3.33, H 6.66, O 3.33, and of course you aren't going to have anything with that sort of formula. So what we do is we just take the smallest number, in this case being 3.33, and divide all these three numbers of moles through by it. So 3.33 divided by itself is 1. 6.66 divided by 3.33 is 2. And then 3.33 divided by itself is 1. This is called the empirical formula. This is the MF means the molecular formula, not anything else. MF is the molecular formula. In order for us to actually do this, if we were given these percentages and we had to generate the molecular formula, we would also have to be given the molecular weight of the molecule, which we actually have right here. And the way to do that, or the way to get from here up to here, is to say, well, what is the empirical formula weight of what we have? Well, that's 1 carbon, 2 hydrogens and 1 oxygen, so that's 12.011. 2 hydrogens is 2.016, and oxygen is 16. I'm just trying to do this without writing anything down, just to save some space. 12.011, 2.016, that's 14.027 plus that is 30.027 grams. That's the empirical formula weight, the result of 1 carbon, 2 oxygens, and 1 carbon, 1 oxygen, and 2 hydrogens. And so the way to get to the formula, the molecular formula, is simple. You do the molecular formula weight, 180.162, divided by the empirical formula weight, 30.027. What you get is a factor of 6. This means the molecular formula is 6 times as big as the empirical formula. Therefore, we've got to take our empirical formula and multiply everything by 6. Therefore, 1 carbon becomes 6 carbons. 2 hydrogens becomes 12 hydrogens. And 1 oxygen becomes 6 oxygens. Alright, and notice that formula is the same as the one up here. So what we've done overall is go from a molecular formula down to a series of mass percents. And then, kind of improvising in, because I didn't think I was going to do this, we figured out how to go the other way too. From mass percents back to a molecular formula. So we've gone both ways. Alright? And hopefully that makes sense. Thank you.